Our solar system is vast. From our own star, the Sun, to Earth is nearly 150 million kilometers, or 1 astronomical unit. Jupiter is 5.2 AU distant, and Pluto up to 48 AU. And the solar system extends far beyond this into interstellar space. We humans cannot travel that sort of distance, at least not yet, but we can and do send our robots and probes in our place. And the results are astounding. The ion-propelled Dawn spacecraft is one of our emissaries that has rendezvoused with 2 asteroid belt objects in its multi-year mission.
The Dawn mission is one of NASA's Discovery Program missions that launched in September of 2007. So it's had a long, circuitous journey from the Earth, flying past Mars and out to the asteroid 4 Vesta, where it spent a year orbiting this small rocky object and mapped its surface and determined its bulk composition and geological aspects of Vesta before leaving the gravitational field of Vesta and traveling for another 3 years out to the dwarf planet Ceres.
Before the arrival of the spacecraft Dawn at Ceres, we were expecting an inert rocking body.
Instead, they discovered a world of mystery and surprise. Dawn has been orbiting Ceres for more than 2 years now, providing us with fascinating views of an alien world. The mysterious bright spots on Ceres appear to be salts deposited on the surface by subterranean activity. Support for this theory can be found in another feature of interest, the bright mountain named Ahuna Mons.
We have looking in detail about the shape of the mountain, and we have compared with what we know from volcanic constructs, and we have found that Ahuna Mons' shape is very similar to that of a volcanic dome that is built by very viscose material.
When we saw Ahuna Mons, we saw that its shape was very tall. It was very tall and had steep slopes. And that reminded us of certain places in the solar system, including Earth and Mars, that had domes that were formed by volcanic activity of very slow-moving, thick material. However, on Ceres, the temperatures are so cold that the same type of magma on Earth and Mars just can't exist on Ceres. So we then concluded that the magma, or the material that's flowing on Ceres, had to be composed of mostly very salty water that would flow at the low temperatures of Ceres. And when exposed to the surface, when they were pushed out onto the surface, they would freeze and form this steep-sided dome. Ahuna Mons is unique in the solar system. There's no other place in the solar system that has a structure that matches that of Ahuna Mons, and it has to be formed by cryovolcanic activity.
Scientists at the German Aerospace Center have used stereo images to create a global digital terrain map of the dwarf planet. Another surprise, a study published by lead author Norbert Schorghofer shows permanently shadowed regions at the North Pole. These are expected to be cold enough to accumulate water ice over long time spans. Future spacecraft visiting Ceres are likely to find freshwater ice there.
So right now we are not only learning about dwarf planet Ceres, but also about planets and small bodies in the outer solar system, like Pluto and its moon. And so we are in a phase in space exploration where we are learning about a new class of object, and we are seeing that these objects are surprising as they have recent features on their surface. These observations tell us Sirius was active in the recent past and might be even active today. And these tell us the importance of sending a spacecraft to a dwarf planet to have a close look at the surface, as we are learning new things that are unexpected.
Dawn is now orbiting only 386 kilometers above Ceres, which is closer than the space station is to Earth. And it will continue to return spectacular views. One of the key technologies that made Dawn such a success was its ion drive.
Ion propulsion allows us to undertake missions which would be impossible without it. There have been previous missions and tests of ion propulsion to validate the basic technology, but Dawn now has made it a reality. Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
Our second deep space emissary has only recently arrived at its destination, the giant planet Jupiter. Juno is our fastest probe to date. Reaching a top speed of 265,000 kilometers an hour, or 73.6 kilometers a second, it has traveled for almost 5 years to reach its target and orbits the poles of the largest planet in the solar system.
Juno's the fastest spacecraft ever to venture into the outer solar system. It's the first to orbit pole to pole about Jupiter, and it's the most heavily shielded spacecraft that we've ever launched. The mission is designed to basically wrap Jupiter in a dense net of observations, completely covering the sphere. So to do that, we need a polar orbit, one that passes over the North Pole, along a line of longitude, and over the South Pole. And we do this over the 37 orbits of the nominal mission, and by the time we're done, we've got orbits separated in longitude by about every 12 degrees. So we completely cover the sphere.
Basically, the interior of Jupiter is nearly unexplored. What we see when we look at Jupiter and all the great, amazing stuff we've discovered about Jupiter is about the moons that orbit the planet. It's about the atmosphere and the enormous weather systems and the great red spot and belts and zones, stripes across the planet, all kinds of really cool, interesting, exciting stuff. But it's kind of skin deep. When we look at Jupiter, we're going, 1% or 2% of the way down into the planet. That's what we're really seeing. Everything else about Jupiter, the deep interior of Jupiter, is nearly completely unknown.
To peer beyond the veil, the suite of instruments on board Juno includes a gravity radio science system, plasma and energetic particle detectors, ultraviolet and infrared spectrometers, and a vector magnetometer.
A magnetometer is, it's best to think of it as a fancy compass. Unlike a compass that just records the direction of the magnetic field, our instrument tells you both what direction the field is in and what the magnitude is. And we can measure that very, very accurately to 100 parts per million. Juno's magnetometer is another in a long line of magnetometers built here at Goddard Space Flight Center, following designs developed by Mario Cunha years ago. Our instrument is between 1 and 2 orders of magnitude more accurate than anything that's flown to Jupiter before. And of course, part of that is the result of the star cameras that we're able to fly with our sensors so that we can determine the absolute orientation in space of these sensors. If we did not know the orientation of the sensor as well as we can determine it with the star cameras, we would lose accuracy in the vector measurement. So we carry 4 star cameras with our 2 magnetometer sensors. These have to be held in the same orientation with respect to each other under very extreme environmental conditions. So we designed what we call a magnetometer optical bench. It's a special structure, about a square foot in size, that is made of a carbon silicon carbide material, almost impossible to machine. But once it's fabricated and the sensors are assembled, they act as one. And that's one of the reasons why we can achieve much higher accuracy than has ever been attempted before.
Studying the magnetosphere of Jupiter is a prime objective.
Magnetic fields have been a curiosity for thousands of years. And so, of course, we know now that magnetic fields are generated by what's called dynamo action, the convective motion of an electrically conducting fluid. Even though we can map the Earth's magnetic field with extraordinary accuracy with satellites in orbit about the Earth, the one thing we can't do is see clearly through all the crustal magnetization that is right beneath our feet. Jupiter is a gaseous planet, hydrogen, helium. There is no magnetized crust that obscures our view of the dynamo deep below. So the exciting part about the Jupiter mission is that we'll be able to image for the first time the magnetic field on the dynamo surface in a way that would never ever be possible on Earth. Jupiter is also the planet with the largest magnetic field. Its magnetosphere is huge. If you were to look up into the night sky, and if you could see the outline of its magnetosphere, which you can't, it would be about the size of the moon in the sky. It's a very, very large magnetosphere. In fact, in the Voyager program, we learned that the magnetic tail, the part of the magnetosphere that is drawn away from the sun, extends all the way out to the orbit of Saturn and in all likelihood beyond. It's a very large feature in our solar system. It's a pity we can't see it.
Of course, a strong magnetic field traps more radiation within its grasp, another issue for Juno.
There's two types of radiation we worry about. One is when we fly through the radiation belt, we get an instantaneous exposure, we call that flux. The other is flying through the radiation belt again and again and again gives us something about accumulation, we call that dose. And so in the beginning of the mission, we fly largely close to the planet underneath this kind of flat donut-shaped radiation belt, and then we fly around it. But eventually we fly more and more through the belts, and our radiation levels, every orbit, get worse and worse and worse. We get over 80% of radiation exposure in the last half of the mission.
For me, the great excitement is the opportunity to look down and get the first clear, unobstructed view of what the magnetic field looks like on the surface of a dynamo where it's generated. It's always incredible to be the first person in the world to see anything. We stand to be the first to be able to look down upon the dynamo and see it clearly for the first time.
Our emissary to the ringed planet Saturn is now in its final year of operation. Its outstanding performance has included dropping a probe on the moon Titan, making extensive observations of Saturn and its moons, even adjusting its mission to fly through the water vapor plumes discovered gushing into space from the moon Enceladus.
Cassini was never designed to look for life in the Enceladus Ocean. But it does have powerful instruments that can be used to look for habitability. So we're looking for the conditions suitable for life. Now Enceladus is a tiny moon, but it's really intriguing. It's got this plume that is shooting out from its south pole. The plume's mostly comprised of water ice, that gets frozen when it's ejected out into space. Most of these particles are coming from these 4 major fractures that we call tiger stripes. Life needs 3 things, right? It needs water, it needs chemistry, and it needs energy. And right now, some of these lines of evidence are telling us that Enceladus has these 3 things. We see some salts, but most importantly, we see organic molecules, things like methane. We also see CO2, ammonia. One of the things that Cassini can look for is molecular hydrogen. This is the smallest molecule that exists in the universe. It's 2 hydrogens bonded together. This molecule can tell us about things like hydrothermal activity going on in the ocean of Enceladus. And this is very important as we start to answer that ultimate question of, is there really life on Enceladus?
NASA's Cassini mission has begun a daring set of ring-grazing orbits, skimming past the outside edge of Saturn's main rings. Cassini is flying closer to them than it has since its arrival over 12 years ago. It will begin the closest study of the rings and offer unprecedented views of moons orbiting near them. Even more dramatic orbits will take Cassini through the F ring, the outer and most active ring, which contains one ring and a spiral strand around it. Cassini will make its final orbit later this year and plunge into the Saturnian atmosphere, ending more than 11 years of scientific observations. Traveling over 10 years and 5.5 billion kilometers, New Horizons is our emissary to the outskirts of the solar system. In a dramatic flyby, New Horizons scanned Pluto and its main moon Charon. The brief encounter amassed gigabytes of data, which the spacecraft took months to download to Earth. Its close-up details of Pluto's terrain generated a great many questions. It looks more complex and highly active geologically than first thought, with solid nitrogen ice forming many fascinating and colorful textures and landscapes. New Horizons captured this high-resolution enhanced color view of Charon just before closest approach. Charon's color palette is not as diverse as Pluto's. Most striking is the reddish North Polar region, informally named Mordor Macula. After such a successful flyby, the mission has extended to include a second Kuiper Belt encounter. New Horizons is set to fly past 2014 MU-69, a Kuiper Belt object currently about 1.6 billion kilometers beyond Pluto. Arrival time, January 2019. As one mission ends, another is about to begin. Bepi Colombo, Europe's first mission to Mercury, is currently being put through its paces at ESA's European Space Research and Technology Centre in the Netherlands. Bepi Colombo consists of several components in a so-called spacecraft stack. Apart from the two orbiters, there's also the Mercury transfer module, which contains the solar electric propulsion engine to get them there.
Okay, what we have here is the MTM, the Mercury transfer module, which brings us, or our two spacecraft, to Mercury, the 3 xenon tanks and the 4 thrusters. And when we arrive at Mercury, this unit will be jettisoned, and then we only have our two spacecraft.
The two spacecraft are ESA's Bepi Colombo and the JAXA magnetospheric orbiter. Mercury is the closest planet to the Sun in our solar system. Yet despite temperatures reaching around 500 degrees Celsius, the previous NASA Messenger mission found evidence for ice at the planet's north pole.
One spacecraft is provided by ESA, which is MPO, we call it MPO, Mercury Planetary Orbiter. And this spacecraft has a focus more on the planet. We want to observe the planet, do remote sensing, characterize the surface, count the craters, wanting to know about the composition of the surface, the interior of that planet. And in addition, we have a second spacecraft, and this spacecraft is called the Mercury Magnetospheric Orbiter, more focused on the environment, and this spacecraft is provided by the Japanese Space Agency.
The Messenger mission found other surprises at the smallest planet in our solar system. It discovered more chemical elements and compounds with small boiling points, known as volatiles, than expected at the surface. Messenger focused on the north polar region, whereas Bepi Colombo and its instruments will cover the whole planet, as well as exploring its gravity field.
One of the special things about Mercury is that it's the only planet besides Earth who has a magnetic dipole field. And so we would like to understand the dipole around Mercury, or how the magnetic field around Mercury is interacting with the Sun. And that's very important for us, because then we can learn for Earth how the Earth's magnetic field is interacting with the Sun. And we have a lot of satellites around Earth which are affected by the solar wind and the interaction. So if we can get some clues about processes on Mercury, we want to learn for Earth.
Bepi Colombo's launch has been set back by minor hardware issues. Now scheduled for late 2018 launch, it is expected to reach Mercury in 2025. With the go-ahead from NASA, the Europa Clipper mission is underway, with the selection of instruments to fly on the spacecraft hopefully in the early 2020s. Its mission is focused on the Jovian moon Europa, believed to hold an enormous ocean of water beneath its icy surface. Europa's proximity to Jupiter and its speedy orbit cause the moon to stretch and contract under gravitational forces, generating mechanical heat within the core and providing enough energy to maintain a liquid ocean. Close inspection of surface areas also predicts that ice movement on the surface, similar to glacial movements, could allow for the formation of liquid water lakes close to the surface. One more place to search for those elusive signs of life.